No, yeah, okay.
Okay, I'm sorry.
Oh,
We
I
are.
was muted as well. I apologize. I'm
Oh,
sorry,
okay.
Ryan, to disappoint.
I was
I'm sorry.
I was waiting for you, so sorry.
Yeah, it was my fault. I was muted too.
Good
See,
luck.
this was. I hope now that this is the last technical hurdle. So let's. De Rose, are you okay? We record you.
Yeah, no problem.
Okay, so it's my pleasure to introduce De Rose. De Rose is a full professor at PUC Rio Grande do Sul, which is in the southmost state of Brazil. Uh, he has been working in the area of parallel scheduling, resource management, and virtualization um, for a long time. I have the pleasure to have known him for, gosh, more than 15 years now. We worked together quite a lot. At the time, I was faculty. Uh, and he's researching, everything from cluster management to virtualization to parallel scheduling for the longest time. He's the founder of the PUC Rio Grande do Sul High Performance Computing Lab, and uh, its leads to this day. The host, thanks so much for coming and giving us the keynote this year.
Thank you very much for the invitation. Good morning, everyone. I hope you can hear me well. Unfortunately, we are having some serious infrastructure problems here in Brazil during the pandemic because everybody is at home like it should, but the infrastructure is not holding up. So I moved to my office here at the university, and I hope this solves most of the issues. Are you hearing me well?
Yeah.
Yes, yes.
Okay, I tried to put my slides. Let me see here. Are you seeing the slides?
Yep, we can see the slides.
Okay, great. I will go ahead. So if there is any problem, please let me know. I'm taking a look at the chat and also WhatsApp. So thank you again for the invitation. It's a pleasure to be here talking to you. And my idea today was to show you what we have been doing in the area of interference-aware scheduling in the last 10 years, how we got to it, what was our motivation, all the steps all the work that we did before today, and what we are kind of heading in the future. And I put in every slide that I have some kind of results. I put the corresponding publication. So if you want to take a look in more detail, you can take a look at that. So I always begin with some background because I think it's important to give some ideas on what was my background, and that helps to understand the point of view that we have as a group here, and why we sometimes go for some directions and take some decisions. So Alfredo already told about the affiliation part. Concerning background, I did my PhD in the Karlsruhe Institute of Technology in Germany some time ago, and it was in the area of resource management in parallel machines. So this was also related to my master degree here in Brazil. So I was concerned about how resources are used and how we can improve resource usage, and this struggle with the user side, improve sharing without penalizing too much the applications. My main research interests are resource management in cluster, computational grids and clouds. Most of the work that I did with Alfredo was in the area of resource management in grids and clouds. Parallel and distributed processing, high performance computing, virtualization, computer architecture. So you can position myself a little bit low level. So it's what I will present today is, of course, the result of the work of many people. I put some of them here. So you see some of the PhD students at the right, and we call ourselves the Resource Management and Virtualization Group. And the main goal of the group is to optimize resource usage to improve ROI, return of investment, while maintaining quality of service. So that would be the main, that's what is written on the wall when you go in. And depending on the time frame, we were concerned with some particular aspects of optimization. So it was already energy in the beginning of 2000s. We deal something with security, and I will show you our efforts in the direction of interference. Platforms that we are interested in, they change over the last decades, but the problem is more or less the same. So if you take a look at multiprocessor, cluster, grid, cloud, edge, fog, so you have usually networked resources and a lot of applications looking for them. So this generic scheduling problem. And that's why I hope that many things that I will present to you will interest you, independent of level or what the kind of work that you do. We did a lot of tool development, basically tools to improve resource partitioning, resource scheduling, monitoring, and maybe the most famous one was CloudSim. CloudSim was developed by one of my PhD students in a cooperation with Rajkumar Bhuya in Australia, and that's why we still use CloudSim to do some simulations, also related to scheduling in clouds and with virtual machines. We did a lot of plugins for CloudSim, so we're still involved in the development of CloudSim. INTP, I will show you today. It's a tool for low-level interference monitoring, and that's also public, so maybe you find also interest to take a look. That's an opportunity to thank my sponsors. So it's not that easy to get federal grants in Brazil. We have federal grants here, but most of our money comes from the industry. So I will use the opportunity to thank HP Brazil, Dell Brazil, and Petrobras. That's our oil company that funds basically most of our projects and students. So, so the beginning of this work relates to the 2013, and it came in the form of HP Brazil talked to us, and they are interested in evaluate container overhead at the time and also isolation. So they were using virtual machines and containers, something that will be at the time a lot of people talked about. So they say, look, take a look at containers. You want to understand what are the trade-offs of moving some of our infrastructures to containers. And the first phase of this project was to do basically some experimentation. So main concern was virtualization overhead, but also some resource isolation. And when they talked isolation, they were more concerned about resource guarantees and also security. we'll talk a little bit more of this different kinds of isolation. And the methodology at the time was very empirical and very simple. At the right, you see here let me see if I can point. You see the stack. So you have a machine, you put some operating systems, you put the containers. Usually, I think that it was Linux at the time. And you put one container with the HP application, and you put another container with some kind of stress source. And we stress several of the components of the hardware. So basically CPU, disk, memory, things like that. And we tested a lot of options at the time: Linux containers, OpenVZ, and bserver. And we expected some results will be worse in virtual machines because the level of isolation, this is the trade-off of containers. We expected a less overhead, but some isolation, but we are really blown away by the results. So they are really very high. I marked some here, some in red. So that represents how much the HP application was affected by the stress test in each of the different systems. So and DNR means that it didn't run at all. So that would be also lead to some security problem because they broke the application that could lead to some form of attack. So the impact is very high, and if you see memory, very high. Disk was already a problem in virtual machines, but disk was high, network was high. So this caught our attention, and the virtualization overhead was minimal. This was already expected. So no overhead to use a container. It's almost like running bare in the real machine. So that was very nice, but it raises a lot of concerns about isolation problems. And they are susceptible to all types of interference. And this, when you take a look more closely, this was related, of course, to the sharing of not only the hardware itself, but also the control structures. Because the containers, if you take some, for example, Linux container, you are sharing a lot of management structure of the kernel of the operating system, and this may hurt performance a lot in some cases. This caught our attention, so we wanted to investigate a little more this uncontrolled competition for the shared resource and what kind of impact that could have on the performance. Because we knew if you, and HP was concerned about this too, if you hurt performance a lot, you end up hurting quality of service, and then this leads to some break in SLA, some system level agreement, and then this also leads to some profit loss or some fines. So the infrastructure will react to that, usually allocating more resources to compensate the loss, and that's also bad because you are kind of putting more resources, and this consumes more energy, and let's go on. So this leads clearly to poor resource utilization. And as I mentioned, users lose profit because if you are running some service, like you are selling something, or in the case of the Dell project that I'll show later, the site was running in some of the cases. So if people get lagged when they clicked for products, they end up not buying anything. So the clients, you may lose clients, and providers have to pay fines. So the provider it's penalized twofold, because he first have to, when the SLA breaks, he pay fines, and second, when he noticed that, he has to react and put more resources. So he was spending more resources and energy to react to these impacts, and that's really bad. And so our motivation from that point, we decided to put some people of the group taking a look of performance isolation. So The problem is not to guarantee isolation of the allocated resources. Like, this is okay. So if you say the virtual machine or the container should only use 4 cores or only 50 gigabytes of memory, they hold on to that. But the idea is to investigate more the indirect impact of these shared resources and control structures. So when you take a look at caches, buses, controller queue, things like that. And this is not easy to predict. So, and if you can't predict that, you may have problem at high level. So I take a code here from the cloud book from Marinescu, and it says to exhibit a predictable performance, an application has to be isolated from other applications it share resource with. Performance isolation is a critical condition for quality of service. That's what I mentioned before. And it needs guarantees so that the provider and the clients can be sure that they will get the performance they asked for, and they bought for, right? They paid for. There are techniques to deal with it. So we took a look at state of the art. At that time, we are here already around 2014, and you see that you can apply some kind of capping. That's basically you take a look at the greedy users and you put some limitations on the critical resources. So you could say, look, as an application, you can use more than 80% of disk or something like that. You can do some kind of round robin. That is, you take a resource and say, I will not allow shared use of this resource because it's really critical. Applications that are consolidated in the same machine, they have to do some kind of round robin. So they have to, you have exclusive use of the resource. That, of course, will penalize performance. But the idea is that if you do this smartly, you are not penalized as much as an interference will cause. And you can do some kind of blacklist. Blacklist is interesting. We will exploit that in the future. So blacklist is basically saying, look, application A and application B, they are very cache intensive. So don't put, let the scheduler know that they are not, they should not put it together. So you could have some blacklist. The problem we will see is that you have to know this in advance, and this list may be really big. So that's not easy to manage. But anyway, the target environment here, to give you an idea what I mean by virtualized environments, you have some kind of virtualization layer, virtual machines, containers, and you have applications that want to use a share of these resources. And the idea is to share this cluster of machines the best way possible to accommodate the machines with the minimal number of accommodate applications with the minimal number of physical machines, so that you are running low on energy, and you are, if you're renting them, you could charge for and you have less infrastructure cost. If you have a private infrastructure, like an university or a company, the idea is basically the same. You want the best return of investment of your resources, so you want to satisfy users with the less amount of hardware possible. So we end up having a lot of applications sharing a node, and that's what some people called consolidated nodes. So you consolidated several applications in the same node. So our preliminary experiments show severe interference among consolidated applications in some cases, so especially with memory and disk. This was already the case in virtual machines. We observed that also in virtual machines. We had some projects with Dell, and they were interested in using this kind of infrastructure to consolidate database applications. So we had very high interference levels sometimes when you have a lot of disk use, and that, so they end up not doing that. So it took them a lot of time to go to virtualized servers that were servicing database applications. Of course, technology improved and isolation mechanisms improved, but there are still situations where we observe interference that really impacts on the performance of applications. So we tried to do more detailed experimentation, and we went in the area of workload characterization, because if you take a particular domain, you see that, and that's really application specific. So if you take a particular domain, like we took some big data applications, Hadoop and Spark applications, Storm, you see very specific patterns. And that's, if you have more information, you can of course optimize better, and you can tune your policies to this specific application. So what we did at the beginning was to focus on very specific domains, try to learn most of we could about the workload characterization of those applications. And we have very interesting, I know I'm biased, but we have very interesting papers on that, papers that have been used by, and we have some citations from Intel, from industry, because they want also to understand what these profiles are. And after you have that, you can do some fine tuning. So for example, with capping, here is a very basic experiment. What is going on here? We are running 3 applications in the same physical node without, and let me see, with no restrictions. So that's the top level, and with 3 different schedulers. So these are, I think, very disk. Yeah, this is disk intensive applications. So what you do is you don't control anything. So you see, you have moments of spikes in green. Here you have spikes in blue, and they interfere each other. So that's the total time that these 3 applications needed to execute in the shared machine. You see this for CFQ and deadline and NOP. So 3 different schedulers. So that's basically the same time. And here at the bottom level, after we understood what was going on and we put some specific capping limitations, this experiment with capping, we could improve performance, execution, and also quality of service. So basically, we are forcing some limitations. We are not letting the application get all the resources that they wanted. This is the capping will also affect will result in some kind of round robin, because if we're capping someone, he has to come back to get it again. So it's kind of interfering also. We are affecting some kind. So it's a mixture of capping and round robin. The results are very interesting. You get some really good improvements here. Here, not that much, but the problem with this is that's really very specific to these applications and this environment, and that's really bad, because we took a lot of time to understand the applications. We had to do some limitations on specific places for specific resources, and this is really not something that we can use in production or something like that. This is more to see that there is space to do some optimizations. We use that as a proof to motivate us to go into that and to look into some more automatic mechanisms. So interference is indeed a very problematic for virtualization. That's our experience. And what people usually do is some capacity-oriented based bin packing algorithm, and that's not taking a look at that. So you end up with some situations where you are allocating more resources not because the applications really need it, in the sense that they need to run because someone was interfering, they are interfering with each other. And if you do some moving, if you do some migration, you could improve that a lot. So that was our goal, to do some smart scheduling, taking interference into account, and to improve the placement so that we use the same set of resources and we get better results. But of course, the problem is already complex, right? You know, that's scheduling crowd. This is already complex without interference, and we already rely on heuristics, so a lot of challenges, right? First of all, try to do it with no previous knowledge of the applications. We see from several cloud infrastructures, you get some requests, you have no idea what the user is running sometimes. So you have to have something that will react to that without any previous information. There are a lot of combinations of these applications because things are moving, right? People are going in, going out, so you are moving the combinations. So you can't do something based on specific pairings. You have to do something that will work because the combinations will be too big. You have to do something that will handle different kinds of combinations at real time and deal with that without knowing in advance who will be staying you at the same machine. Here's a tough one. You have to consider workload variations. So our early work I'll show you is based on static classification of applications. I take a look at you and say, you are hungry for memory. And that's what you are labeled for the whole execution time. And that's not always true. Some applications are very sensitive to workload variations. For example, we'll see some streaming applications or some web applications that will have more clients, and then we'll change some of these classifications. So that was also really tough to handle. But the long-term goal is to go for a new family of dynamic interference-aware schedulers for this kind of virtual environment. There is a fundamental problem, and that's to measure interference. So we have a lot of tools that monitor things, and that's usually related to usage. So how much memory someone is using, how much processor, but how to try to understand the interference impact, the impact on the shared resources and control structures of the hardware. So, and this is fundamental because you want to understand how applications will affect each other. So, and that's really tough, as I said, for all possible combinations. That could be in some cases. We had some examples from Dell. You have hundreds of applications running in a cluster, and that's also tough for new applications. So our take is an indirect approach. We use the background that we had on operating systems, and the idea was to measure how one application affects the hardware that we have. And based on that, based on these stress levels, we infer the impact that it will have to others. So that's the idea, to do this in the indirect way. And for that, we develop a tool. It calls the interference profiler. It's an instrumentation-based profiler to give these levels during execution. It uses low-level profiling to create an application interference profile. So basically what we have here is you do some instrumentation of the OS, and you work with hardware controllers and some control queues and some hardware counters that we have. The nice thing is you have a lot of these counters in modern architectures, and the new ones, they allow you to see the impact of the specific application, and this is really important to us. That's why this tool is not able to run in older machines. We use, when you look, for example, in a cache counter, you can see specifically how an application is stressing the cache or this specific counter. So this way you can have levels of interference for specific applications. All the models will have more generic counters for the impact on the cache, but we would have difficulties to see what application is caused most of this impact. So we began with we tried a lot of things, a lot of different structures, and we had versions of IntP with 17 metrics, and this was of course too much. So we tried to reduce this, and we end up with 5 metrics, and that's basic what's showed here in yellow. It's a storage metric, a network metric, scheduling, that means processor, scheduling, cache, and memory. So that's what we reduce these metrics to. Some of them use several structures and counters, and if you are interested on that, you can take a look of the paper. But the important thing here, we are measuring stress. So the stress level of an application. Here you have an example, and sorry for that, here's some comments. I was asking my colleague what would be the gray line. So I didn't get this answer in time, but anyway, a lot of this work was done by the PhD students. But what you can see here is the lifetime of the application and how this stress. Here we have a version with more than 5, so that's probably an old picture, but how these metrics behave along the execution. So let me take someone that I know. CPU is easy. So you see, and this is a normalized value, you see that in CPU is not hurting the architecture too much in this example. And it's basically constant. I have some warm up, it's kind of constant during the execution time. If you take LLCOCC, that's a cache metric. You see that.
Just to remind you, we have about 15 minutes or so for you.
Okay. Left, you mean, right?
Yes.
Okay.
15 minutes left.
You see that this metrics behave differently. So you could take a look here and say, look, take care. This is orange. This is stressing the cache. So we did this for a big data scenario where we knew the applications for this was recurring applications in a cluster, and we classified the applications based on the IntP metrics, and we clustered them. And what we end up is we could build a blacklist for the scheduler, and we gave the yarn scheduler that the scheduler usually that's used in this kind of scenario. We gave the yarn scheduler information on people that people is good, on applications that he should avoid in the same node. So, and we get very good improvement. Of course, we knew the applications, we spent a lot of time investigating them, we built this list, and we did this in an offline methodology. So this is not applicable to online. You need to know the applications in advance, but there are cases where you can do that. So this is interesting. But we already saw some problem with workload variations. This is big data. You have some streaming applications. We labeled them for the whole execution time, and this was something that was bad for some applications because along the time, and you can see this here, they may change. So they change some of this. So if I label someone, oh, you are cache intensive, at the end here, it's not anymore. So I could use this information to improve the scheduling even more. The second result I want to show you is a result from the Dell project. And here we have another interesting factor. They were interested in web applications that are multi-tier. So multi-tier applications are very common in web applications. They have several modules, and these modules communicate to each other. So the problem here, you have an additional thing to consider, because you have if you see interference as a repulsion force, so saying, look, don't put both these models together, communication can be modeled as an attraction, because if you put these modules in different nodes, they will suffer because of communication. So this is very interesting. We model this. And here because we have now two metrics, we measure the impact. What is worse for an application? To split the communication part and have more communication overhead or more interference overhead in some specific resource like CPU. So we define a setting of placing policies. So you could take a look at the paper. I don't think we did a very good job in this picture, but what's basically saying here, if you have interference, if you are the scheduler and you have interference in two applications, and you're saying, look, if it's disk, split them because disk is hurting too much. If it's CPU, let them together. That's not a big problem in this case. If you have non-interference, no, you can let the scheduler do the capacity planning. That's okay. And if you have both, if you have attraction forces and if you have repulsion forces, because you have communication and interference, do split them for disk. Disk is very critical. Split them for cache. So giving the scheduling specific information where to do repulsion and where to do attraction. So that's a paper. You can take a look if you want more information. So here, basic results comparing both metrics, a model with reduction, with repulsion and attraction, to other policies that state of the art, they only do interference or only do affinity. So you can see you can have very good results if you have less nodes. If you have more nodes, then the scheduler have space to do more, accommodate this application better. But the idea, as you remember, is to reduce the number of nodes to save on energy and on resources. So the main finding is that the results were very interesting opportunities, but again, offline methodology, need to know applications in advance, very, very restricted. So how about dynamic? Again, we noticed that in dynamic cases, this would hurt scheduling. Here we have one application example where things changed. If you split this in two, you see some metrics are low for the first part of the execution and they begin to be high after that. So the message is we need a dynamic interference profile. So we need to change these labels during execution. Here we have an example, an application that we labeled moderate use of CPU, low memory, absent disk use, absent network use, and high cache. If we split in 4 execution moments, we see this change over time. And that was an opportunity to improve scheduling any further. So we are now exploring this dynamic interference profile, but this is challenging because you again, how often should we sample this? How often should we split, analyze the application? That's the best cost benefit ratio for that? How to set these thresholds? What's the difference for medium or high for a specific class on application? Again, very job dependent. So we saw some initiatives with artificial intelligence and we tried to experiment with that. So here's a paper recent paper that do some experimenting with some artificial intelligence models. That's not our domain, so we are a little bit skeptical about that, but we had some interesting results that we could do some of this splitting and some of this online classification at runtime. It is still on early stages, only for maximum number of jobs. It means this takes a lot of time too. If you have a lot of jobs, you have to classify them several times during execution. So you have to take a look on the overhead. Another thing that we are investigated now that also applies machine learning is proactive scheduling. So if things are taking too long to grasp, how about trying to, this specific to the workload variation, how about to see how the workload will behave, or try to predict the workload behavior in the future, and try to begin calculating a better placement ahead of time. So basic to hide the latency of this more time-consuming placing model. So we are doing some experiments with that. We are using some regression models. This is already working very well in other areas. So we tried in our domain, and we also get very good results. You see this here for a particular, red is the actual variation of the workload, and you see different results for different machine learning techniques here. We are surprised. They are pretty good. Of course, this is again very dependent of the application, or how much data you have in the past, and how much in upfront you want to predict the future, right? But we think that we have potential to use that here, and to improve to still use some complex placement models, but hiding the latency, trying to do this in advance before the problem arrives. This is also being used, and we have another student working on that, to reduce virtual machine allocation. For example, to try to reduce
5 minutes the hose.
5 minutes. I'm concluding. So for example, there is a problem that you sometimes, providers sometimes, because they are afraid of abrupt workload variations, they do some over provisioning. So they give more resources that the application is actually needed to have a buffer, and this has a cost. This kind of methodologies we are using also to predict that some is changing, so to run a little bit more without this buffer, and when things we see a tendency that things will change, we allocate more virtual machines. And the same thing to improve the to avoid under provisioning. So we see that something will drop, we will begin removing virtual machines, so that we have a better use of the infrastructure. So coming to my final remarks, so we believe performance interference may have a big impact on resource usage and quality of service. This, of course, may vary on the domain, but we observe that in several scenarios, and this is really something that we think you should take a look at in your problem. There are several mitigation techniques that could be applied to that, depending on the level that you are, and the level, the workload and the environment characteristics. If you are, for example, if you are virtualizing a lot, sometimes you don't have these low-level metrics. So if you are very low, you have the metrics, but you don't have the time to do something because constraints are smaller. So you have to take a look at your specific conditions, but you can use, and these things work, you can do some capping, some round robin, some blacklist in the static area, and you can try some interference profiling. That's what we are advocating. You can, the move to dynamic, we think it's inevitable because things are going in this direction. So the nature of the environments, and if you take cloud and things like that, and you also you can't rely a lot on information, because you have situations you don't have any information. You have only what you see from at running time. So you have to deal with that in some cases, and we think that's possible anyway. And we were a little bit skeptical, but our first impressions of artificial intelligence used in some specific cases, especially in proactive scheduling. We think that this is a direction to go, and this could really help. So I hope that I meet my time constraint. Don't make the scheduler mad with me. And I hope that I gave you some interesting insights that you can apply in your particular problem. And I'm now open to questions. Thank you very much.
Thank you, De Rose, for the interesting presentation. Let's see if people have a couple of questions. We are on time, but let's make space for a few questions. Really, the conversation is really the important part. Anyone has? So I have one, De Rose. I was looking on the labeling and all of that, and I think that's a very interesting approach. But how can we kind of better automate and learn that, right? Because the solution is interesting, but to be able to apply large scale and like labeling, yeah,
it's tough. There are some situations you know your workload very well, so that's more feasible. So in this Dell project, they are running things in production. It's very close environment. You probably have something Google as well. They are recurring jobs. They run every time, and you know more or less the workload. You know how workload behaves for these jobs. So in this kind of situation, then you can do some smart labeling, even with thresholds. So that's okay. That will do the job. But if you go to something more broad, like a cloud provider, you have no idea if people are running your infrastructure. Then I think this machine learning approach could be interesting. The problem here is you have to train this, right? And I'm probably not the best guy to explain that, but I mean, it changes a lot. If you have to have a lot of input, so you have to take a lot of again, you have to take the applications that usually run in infrastructure. You have to vary the workload, and you have to have samples here. We trained this with 50,000 samples, but we use specific applications, we use specific workload variations. They are probably not what you see in the real world. So, but I agree. This is an open problem. This is just a beginning here.
So I think Roberto has a question. Roberto, if you unmute, maybe you can just ask and go ahead.
Hello, hi, thank you very much. Just a question / advice. I've seen that you benchmarked many disk schedulers, but lately I've seen that in Linux distribution, the DFQ scheduler has growing interest, since it should have lower latency and be able to provide better bandwidth for many different parallel and concurrent requests. So do you think that it can help your research or improve the results that you obtained here? Thank you.
Of course, what you see here, this is data from 2015. So, and it's very the reason I put this here is just to show you what motivated us. I think things really improved. The technologies, the virtualization technologies improved, and of course the schedule has improved. The point is, we don't think this solved the problem at all. So, but I agree with you. People are doing something. So when we compared here with this Dell study, when we compared with different schedulers here, we saw some people already doing interference-aware scheduling. So this is evolving to production. The nice thing of this study is that we, at the time, this is published in 2019, but this is a study from 2017. At the time, we are the first ones that combine these two metrics. But you see, state of the art are already doing some interference and some affinity. We could take a look at this schedule. Maybe he's already doing something regarding interference. But sure, things are improving.
Thank you very much.
I don't think it's really a solvable problem, because I think that's when you share. I mean, that's a fundamental thing, right? When you share things, you have contention, and okay, you can deal with the level of contention, but there is always something that I think we can do at scheduling that will improve the situation.
So I think maybe we could quickly take a final question from Pila. Do you want to say your question, Pila, please?
So my question is that it's regarding all the new accelerators that we are getting into the cloud. I'd like to know if we can mitigate the interference of those different new accelerators in a way that the problem is still treatable.
I'm not sure I get the exact problem that you were mentioned, but every time you change the hardware and you share something, for example, what we are so investigating, HP is so interested in another project in investigate how you can share these accelerators, because usually put one accelerator or two in a very high server, in a very high-end server, and of course a lot of applications wants to use that, right? And then you end up with the same problem, in the sense that you could do you don't want to lock applications to the accelerator. You want to share. So how do you share this? You do some time sharing, or because then you have control mechanisms in the host that are being shared, and also in the accelerator itself. So we saw some works about NVIDIA dealing with that. That's a particular low-level version of the same problem, I think.
Thank you.
So definitely the answer is yes. I think you can apply the same, and you can try to move. If you think two workloads are stressing the same GPU, you can move the GPUs to other ones. So in the same host or in another host.
Perfect. Thank you.
All right, so let's move on to the technical sessions. I want to thank again De Rose for the great presentation.
Thank you very much, and thank you for the opportunity to present.
Thanks so much, De Rose.
Thank you.
You want to take it from there?
Yes, thanks. So we will start with our first technical paper. The title